Very good morning, dear friends. Myself, Dr. Vikrant Sudhakar Payekar. I am working as assistant professor in Gokhale Education Society's Arts, Commerce and Science College, Jawar, Palghar. Today, we will be starting with the new topic, that is stereochemistry. As this topic is very interesting and one of the very important topic in the subject of organic chemistry. Today we will deal with some of the basic concepts related with the stereochemistry and molecular chirality. Let us start first with the very basic concepts. What is stereochemistry? If we ask the question, then the answer comes, it is the three-dimensional arrangement of atoms in the space. So basically in the stereochemistry, we deals with the arrangement of the atoms or groups inside the space. So this particular arrangement help us to know various different properties of that particular compound. If we ask for another definition, what is stereochemistry? Basically it is the study of properties of stereoisomers. As we know that stereoisomers is nothing but the compound or basically isomers having same formula, but they differ in the connectivity in terms of position of atoms or groups inside the space. As we know that stereoisomer is one of the classification of isomers, as we have studied in our earlier classes that stereoisomers are again divided into two types. One is the conformational isomers, where you will find the change in the structures of two isomers with a connectivity of their single bonds, like in case of the cyclohexane, chair and boat conformations. So these are the conformational isomers. While configurational isomers, they are having the terms which is related with the non-superimposable mirror images. If the configurational isomers are having non-superimposable mirror images, if two isomers are non-superimposable, then they are called as enantiomers. And if they are not superimposable mirror images of one another, then they are called as a diastereomer. Remember these two classes, enantiomers and diastereomers. If we want to see the historical perspective, how we have come to understand the optical activity of these stereoisomers, then in history, as we know that in the 16th century, the scientist Christian Huygens has been able to find out the plane polarized light. So if you ask the question, what is plane polarized light? Then it is the light which contains the plane or which vibrates in only one plane, that is being called as a plane polarized light. Because if we ask what is the difference between ordinary light and plane polarized light, as we can see, this is a ordinary light, that is sodium lamp. If we see that if it's sodium lamp, it will have the light which is vibrating in all the planes. Here you can see, so it will vibrate in all planes. But if you pass it through the filter or basically prism, then we will get a light which can have vibrations in only one plane. So that is being called as a plane polarized light. And when such a plane polarized light, if allowed to pass through a sample cell which contains your compound which is dissolved in the solution form, then what will happen, once this particular plane polarized light will pass through this particular sample cell, then you will get a rotation, that is being called as a optical rotation at detector level. So that particular phenomena will be responsible for the optical activity of that particular compound. As we know that in the mid-century of 17 and 18, the scientist Jean Biot is able to find out first time that the compounds contains optical activity. So remember that in order to study the optical activity, this historical background we must know how this particular plane polarized light, when passed through a monochromator or filter, then what will happen, the compound will rotate the plane polarized light in the different directions. Okay, if you observe that that particular light has rotated the plane in the clockwise direction, then we say that that particular compound is having dextrorotatory, that is plus when you have the rotation in the clockwise direction. And if it is in the counterclockwise direction or anti-clockwise direction, then we used to call that particular stereoisomer as the levorotatory or minus. For clockwise we used dextrorotatory, and for anti-clockwise we used levorotatory. So this particular experiment is help to understand the optical isomers which are present in the compound. Then we try to find out what is optical activity. Basically, optical activity is nothing but it is the ability of the compound to rotate the plane polarized light. So that particular phenomena is called as optical activity. If you have your compound which is being rotating a plane polarized light in the either clockwise direction or anti-clockwise direction, we call that particular compound as a optical active. If you observe that if your compound is dextrorotatory, so in case of the dextrorotatory, in last slide only we have seen that for dextrorotatory compound you will observe that it will rotate the plane polarized light in the clockwise direction. And for levorotatory compound, it will rotate the plane polarized light in the counterclockwise direction, or we used to say that it is anti-clockwise direction. So the optical activity will be of two types. One is dextrorotatory and another is levorotatory. Then we will see the term stereocenter. What is this particular term? Stereocenter. As it is being already known to us in earlier classes, we have seen a stereocenter is nothing but the center inside the compound which is being having the four different atoms or groups which are connected to one another. Okay, if you can see this particular structure, this particular is the stereocenter. For this particular stereocenter, what will have observed that this stereocenter is attached to the all the different groups 1, 2, 3 and 4. So all the four groups attached to that particular carbon will be different, and we used to call that particular carbon as a chiral carbon or a symmetric carbon. So these two structures where we can find the stereocenter. So remember what is stereocenter. Then we will try to find out what is term called as a chirality. So chirality is the term which is related with the molecule which are having two structures. Okay, so what are these structures? When a molecule is having non-superimposable mirror images, then we will find the term chirality. How can we say that? Suppose if the structure and its mirror images are non-superimposable, then we can say that the molecule is chiral. Okay, just like our hands, our right hand and left hand, they are not even superimposed on one another, although they are mirror images of another. Okay, just like that, if we try to put our right hand gloves in the left hand, then it will not fit. Okay, so in the same way, in case of the chirality, in order to have your compound to be show chirality, they must be non-superimposable mirror images. Means original compound and the mirror image, just like our hands. If we try to put it on one another, they will not match. Okay, so we can say that our left hand and right hand are non-superimposable mirror images, just like this. So this is a superimposable. when I put like this, but this is a non-superimposable. So remember this particular thing in case of the chirality. I hope so you have understood the term chirality. Then we say we will try see what is achiral, means which is not chiral. So molecule is said to be achiral when that can be superimposed on its mirror images. So this particular thing will right now will be called as a achiral because it is superimposed on one another. So what we can see in case of the chiral compound, it will rotate the plane polarized light. Okay, chiral compound will rotate the plane polarized light either in the clockwise direction or in anti-clockwise direction. But in case of the achiral compound, it will not rotate the plane polarized light. Remember that. What is the difference between chiral and achiral? Then let us see the term polarimeter. As we know that it is the device which is used to measure the optical rotation. In the previous slide we have seen the whole diagram of the polarimeter. So basically it is the device by which we can measure the optical rotation of chiral compound, because chiral compounds can only give the optical rotation plus or minus. Then let us see the term enantiomers. So what are the term enantiomer is called as? Enantiomers are basically non-superimposable mirror images, right? Its objects and its mirror image, they will not superimpose one on another. So a compound that is chiral must have enantiomer. If your compound is chiral, then it must have enantiomers. Remember that enantiomers are the two compounds which will have the optical rotation which is equal but in opposite direction. Suppose one of the enantiomer is having plus one, then another will have in the minus direction. So they will rotate the plane polarized light in the same magnitude but in opposite direction. In case of the enantiomer, if you see its physical property, all the physical properties just like boiling point, melting point, refractive index, solubility, density, they will be all same. So in case of the enantiomer, it becomes very difficult to separate the two enantiomers. So remember what is being meant by enantiomer. So you have to remember this particular term. Enantiomers are non-superimposable mirror images and they will rotate the plane polarized light but in opposite direction. This particular thing you need to understand. And in terms of the properties, they are having same physical properties. Let us see these two structures. Basically, when we see the structure, we must have to find out whether this particular carbon. So this is a chiral carbon which is attached to the 4 different groups. All the 4 groups are different. So as your compound is having one asymmetric center, so this is a chiral compound. So it must have 2 isomers. Okay. So what if you want to find out this particular structure and this particular structure, if we try to put this structure on this structure, they will not superimposed, just like this. They will not superimpose. If I put left side structure on the right side, they will not matched, right? So these two structures will be called as a enantiomer. So this structure will have the optical rotation, let us say plus, and then this will be have the minus. That we have to remember in case of the enantiomer. Then let us see the term another diastereomers. So what are diastereomers? These are again a stereoisomer, as we are studying the classification of stereoisomers. That are not mirror images. Diastereomers are not mirror images of one another, and if you see the physical properties of these diastereomers, they will have all the different physical properties, like they will have the different boiling point, melting point, they will have also the difference in the solubility. So it is possible to separate the diastereomers. So remember, in case of the diastereomer, they are not mirror images. Then let us see, for example, suppose if your compound is having two chiral centers. As we know that if your compound is having one chiral center, then it must have two stereoisomers. Okay. So as we know the formula, in order to calculate the number of isomer, 2 raised to n, 2 raised to, suppose n is equal to 1, so you will have the two isomers. For example, if our compound is having two isomers, so n will become 2, so 2 raised to 2 is equal to 4 stereoisomers. Okay, so in that case, let us see how can we find out. For example, in a compound which is having two chiral carbons, then in that case you will find 4 stereoisomers. Out of that, two structures will be enantiomer and another two structures will be enantiomers. So you will find two pairs of enantiomers. Okay, so these two pairs will be diastereomers of one another. These examples already we have seen in case of the 2-bromo-3-chloro-butane. So we are having these two carbons, one, and these two carbons are chiral one. So you will have 4 stereoisomers of one another. Then we will see the term racemic mixture. Racemic mixture is the mixture where you will find the two isomers which are equimolar. So you will find the 1:1 mixture of both the stereoisomers or enantiomers basically. So that particular mixture is called as a racemic mixture. Remember, in case of the optical activity, the racemic mixture will be optically inactive because it will have the compensation factor. The rotation made by one of the enantiomer will be cancelled by the another enantiomer. So racemic mixture will not have any optical inactivity. So remember this particular term. Notations used are D and L. If you have the racemic mixture, then you will observe that plus minus. So already one will be plus, another one will be minus. So this together will be called as a plus minus. Okay. So remember that when you have the racemic mixture, its optical activity will be 0. So it will not be optically inactive. Let us see example. Suppose if you are having the mixture, let us say 2-butanol. So this is a one enantiomer, this is another enantiomer. So what will happen? One enantiomer will rotate the plane clockwise direction with 13.5 degrees, while another isomers will rotate the plane in anti-clockwise direction with minus. Suppose these two enantiomers are present in one particular solution. So overall optical rotation for 2-butanol will be 0 because the rotation made by this particular isomer will be cancelled by this isomer. So this particular optical activity will be 0. Plus 13.5 minus 13.5. So overall it will be 0. So remember, in case of the racemic mixture. Then let us see the term specific rotation. As we know that it is being denoted by the sign alpha. So what is specific rotation? As we know that whatever the angular rotation observed in the polarimeter, that is plus or minus, that particular is called as a specific rotation. As we know that a optical activity of any compound, or basically chiral compound, will depend upon the concentration, and concentration is always taken with just like 1 gram per ml, and path length of sample cell, the solution in which we are taking the sample. So it is always been taken in the decimeter. So it is calculated with this particular formula. It is nothing but the ratio of observed optical rotation divided by product of concentration and path length. So on the polarimeter detector you will find that particular specific rotation. Either it will be plus some degrees or in minus some degrees. These terms are already familiar to you. As we have seen the examples of different chiral centers. As we know that carbon is having chiral center when it is attached to the 4 different groups, then it will be called as a chiral, and this particular carbon will be called as a asymmetric carbon. Then nitrogen, as we have seen, it is not only molecules, the ions will also have the chiral center. So nitrogen is presently attached to the 4 different groups in this structure, so it will be also chiral. Then in case of the cis and trans isomer, just like a 2-butene, so they are also having the chiral centers, remember, as they are being shown with the circles. Then let us see the term molecular chirality. This is the basic thing we have seen till now, but with this particular chapter we are having the first topic, that is molecular chirality. So when we called as a molecule to be chiral, as we already know what is meant by chirality. If a molecule or its ion will be called as a chiral when only when it will have superimposed, it will have non-superimposable mirror images, means its object and mirror image are not superimposed. Just like this example we have seen earlier, these are the 2 enantiomers, these are non-superimposable mirror images, right? So this is then and then it will called as a chiral. Your object, this is my object and its mirror image, so this is a mirror image, but if I try to put this on one another, they will not superimpose. Superimpose means what? They will not match on one another. So that particular compound will be called as a chiral. And remember, in case of the chiral compound, it will be optically active. In order to have the optical activity, your one of the isomers must be in the higher percentage than another. So we know that that particular chiral compound will be either dextrorotatory or levorotatory. In case of the compound which has only one stereo center, means only one asymmetric carbon present, then for that you will have 2 structures. If your compound contains one asymmetric center, then you will have the 2 stereoisomers, and these 2 stereoisomers are called as the enantiomers of one another, right? Remember. Then suppose if you have the molecule with 2 chiral centers, if your compound is having 2 chiral centers, means how many isomers you have? 2 raised to 2 is equal to how many? 4. Okay. Example is tartaric. This particular structure is quite well known to you. So this particular tartaric acid, so it will have 2 stereocenters, because this particular carbon and this particular carbon will be chiral. It will have 2 asymmetric carbons. So basically how many structures are possible? 4. First structure is this one and second structure will be this one. Try to find out what is the difference between these 2 structures. Of course, we can see these 2 structures are mirror images of one another. If I put a mirror in between these 2 structures, what I will find? These 2 structures are mirror images of one another. But what I can observe, they will have the optical rotation in the opposite direction. If suppose one is having plus, another will be minus. So when you have the same structure with same magnitude optical rotation but in different direction, what these structures are called as? Of course, enantiomers, and as we know that enantiomers are optically active. Let us see another 2 structures of this. So these 2 structures, what you observe? Both the OH groups are placed on the right hand side. Here you will find that they are placed in the opposite direction. But for this structure, you will find that both the groups are placed in the either in one structure on the right hand side and another structure on the left hand side. So what you observe for this particular 2 structures, they are again mirror images of one another. But what you find, if I pass a plane which is passing in between the 2 structures, so whatever the structure present above the axis and below the axis, they are just like a mirror images of another. So what will happen? The rotation made by above part will be cancelled by the rotation made by the below part, because overall optical rotation will be 0. So remember, when your molecule is having any symmetry element, just like a plane of symmetry, then what will happen? It's optically become inactive. Suppose if your molecule is containing mirror plane, that is plane of symmetry, then meso inactive. So that particular structure will be optically inactive. See, in case of the tartaric acid, we have seen 4 stereoisomers, 4 structures. Out of that, 2 are optically active, but 2 are optically inactive. See the case. Even if your molecule is containing chiral center, but still it shows optical inactivity. This is a very important point which is to be noted, that in case of the mesotartaric acid, even though it contains 2 stereocenters, but because of the presence of plane of symmetry, that is symmetry element, the optical activity is 0. Means we can say it is optically inactive, that is achiral. Remember, so 2 structures are optically active and 2 structures are optically inactive because of the presence of plane of symmetry. Now, till now we have seen that in our mind, till now it was very clear, if your molecule is having a symmetric center, then it must be optically active. But in case of the mesotartaric acid, we have seen that molecule is completely inactive. We have seen that. But now we are going to see some molecules, even though they do not contain any chiral center, but still they show the optical activity. I am repeating, here onwards we are going to see such molecules, even though they do not contain any chiral center, any asymmetric carbon, but still they show optical activity. The family, first example is substituted biphenyls. As we know that biphenyls are the compounds where you will find the 2 phenyl rings are attached by means of only one single bond. So as we know that the whatever the single bond present in between the 2 rings, it is a movable, that is being called as a pivotal bond. So in case of the biphenyl systems, if it is not substituted, planar biphenyl, there are no substituent present, then what we will observe, both the phenyl rings are present in the one plane. But the moment you have the substituent present at ortho positions different, then that what will happen, because of the steric hindrance, the optical rotations becomes impossible. So what will happen, you will find one of the biphenyl ring is in this plane and another will be perpendicular to it. So movement becomes restricted when in case you have the substituent, just like see for this particular structure. What you observed, here is a one substituent and here is another substituent. Here is one substituent, here is another substituent. So when you have the substituent present at ortho position in the same ring, at above side is different and another side is different. In that case, you will find that the molecule may show the optical activity. So that we'll see in the coming sessions. But remember that biphenyls, substituted biphenyls may show the optical activity. So it is optically active, even though it does not contain any chiral center. Then allenes, as we know that allenes is just like a cumulines, we are having the consecutive carbon-carbon double bonds. So these structures also can show the optical activity when your terminal carbons are having unsymmetrical substituent present. Here you can find A and B, means A and B means what? A is something different group and B is something different group. Suppose A is chloro, B will be bromo. And in the same case, if you have here the another substance, so here you can see the stereochemistry. See the position. This carbon is in one plane while this particular carbon is in another plane. So again, just like this one. So it is a this compound. So this particular structure will also optical active. So remember the molecules without chiral center. Which are the 2 classes? One is substituted biphenyl and another is allenes, which I have already explained this particular part. The present means in our mind it should be very clear that The presence or absence of chiral center is not a sufficient property being to be optically active. It is not just like that. If your carbon is containing chiral center, it means it should be optically active. So it is not a thing. So presence or absence of chiral center is not a sufficient condition. This is to be very noted, this particular line. Since what we need to remember from this particular session, that in order to be chiral, a molecule and its mirror image are non-superimposable. Remember, if your compound need to be optically active, they should not superimposed. Once they get superimposed, your molecule become achiral. Just like this example, already we have discussed. So what is the chirality? In case of the chiral compound, they are non-superimposable. So these structures are optically active. For a chiral molecule and its mirror image, they superimpose. Superimpose means whatever the bonds and atoms present, they will match to one another. So in that case, your molecule become achiral, means optically inactive for this particular molecule. So these two structures of one another. But if I rotate, what will happen? If I rotate this particular molecule with 180 degrees, so what will happen? This 2 will match on this 3 will match on this structure will match on this. So what will happen? It will become achiral. Just like in the case of the mesotartaric acid, we have seen, even though it is not matching, but because of the plane of symmetry, that particular molecule. So mesotartaric acid is the example of achiral. Achiral means your compound must be optically inactive. So go through these particular sessions very carefully. Try to understand the different terms what we have seen. What is enantiomer? What is diastereomer? What is chiral? What is achiral? What is optical activity? So these things, once you understand, then it becomes very easy to understand the further concepts related with the topic. Thank you very much with this particular session. We will meet in the next session. Thank you.